This is Jim Hendershot again, presenting lecture number 13. This lecture covers the insulation systems that are required for the stator phase windings for these three machines, and these the level of insulation is based on the operating temperature requirements and the voltage requirements. Now, grid machines are designed. Some grid machines are designed for generators, are designed for ultra high voltages, 70,000 volts AC. But the motor types discussed in these lectures are intended for inverter operation rather than high voltage grid power or even battery power applications, so the voltages are much lower. The voltages for these motors are all based on the ratings of IGBT transistors, and so the max voltages go to about 2,800 volts. There's development work going on to extend this up to 8,000 volts. I don't know what the status is, it's not my expertise, but ultra high voltage machine insulation systems for grid power requires very special insulation materials, which we're not really going to discuss in this. But for the machines that we're going to talk about, we use the enameled magnet wire for insulation of the magnet wire from conductor to conductor, turn to turn, and then Nomax and Kapton slot liners, and then varnishing using VPI or trickle varnish techniques. Trickle varnish is very widely used for high volume motors, seems to work well. A little preheating, and then trickle the varnish out nozzles on the interns while you rotate the rotor, or rotate the stator, and then the heat and capillary action sucks the varnish into the in between the conductors down the slots, and there's very little mess and cleanup with this. And for larger motors, they're all VPI insulated. High voltage machines use these, ultra high voltage machines uses mica and bakelite and various thick slabs of insulation materials. The average dielectric strength of most insulation materials is at least 1,000 volts per mil, and many of them are up as high as 4,000 volts per mil. The motor voltage classes varies with vendors and countries, but low voltage is considered under 480 volts AC. Medium voltage is 481 to 6,000 volts AC. High voltage 6,001 to 20,000, and ultra high voltage is 20,000 to 70,000. Simple basic considerations for insulation systems. The stator phase winding must be insulated against ground shorts and turn-to-turn shorts. Turn-to-turn shorts are insulated by the enamel coating on the conductor, or higher voltage they're done by the turn-to-turn shorts are insulated by wrapping tape around the magnet wire. Ground shorts are prevented by the slot insulation, slot liners and end boards. Slot liners are frequently cuffed at each end, similar to the cuff of a dress shirt collar, so that the insulator stands up on these cuffs on the ends, eliminates the need for an end board, and then as long as the cuffs never get crushed by forming of the end windings, that supports the end winding and keeps them off of the a distance away from the end of the core equal to the height of the cuff. The other method for lower voltage, which is a very popular system, is epoxy coating of the stators using either electrostatic methods or fluidizing methods. That's aerated methods. And these epoxy coatings are very good for thermal conductivity because they're in direct contact with the steel core, and the coils are usually in direct contact with the epoxy with minimum air gaps in between. So the thermal conductivity from the heat source from the ohmic losses in the windings is very good. There's very few air gap insulating gaps. The other method that's used to insulate cores is coil forms, or what's known as molded bobbins that go around one tooth or multiple teeth. And these bobbins could be made out of they're commonly made out of nylon with glass filling in it, but you can improve the thermal conductivity of those with putting some other materials in them, like aluminum oxide, something like that's still a good insulator, but improves the thermal conductivity. Now, phase shorts are prevented by extra insulation, added insulation. You could take the slot liner material and cut it into strips and put it in between the phases in the slot, and in the end turns you use fiberglass sheets, woven fiberglass sheets of insulation material that you put between the end turns, the phases in the end turns, so that you don't have big potential differences between phases. This is an excellent picture of all these things that I just discussed, provided by Fabrico. They provided this kindly. They're a division of EIS, which is a distributor all over North America that distributes all these materials that you see in this picture here, all different slot liner materials, lacing materials, and all sorts of the components that you need to insulate a stator. There's a few things that are worth pointing out. Here's the slot liner right here. These don't have to have cuffs on them, but they're longer than the core, so they still keep the coils away from the face of the core. Then you have, these are called top sticks or slot wedges that go over the top. That's to keep the conductors from coming out of the slots. Obviously these are the coils. These coils can be made up of multiple strands in parallel, or maybe single strand per turn. That could be just a lot of turns for a high voltage motor, or that could be a low number of turns with parallel strands. It looks like, if this is the lead coming out of it, looks like it's a combination of both. It looks like there's several parallel strands per turn, this being a turn. And this is some sleeving that you would put over the pigtail. When it's magnet wire coming out of here, it's called a pigtail. But then you attach leads. I guess this is not sleeving. That looks like that's a lead wire that's been attached to it. What does it say here? A slot liner. Yeah, lead. Okay, that is sleeving over the magnet wire, but that could be hookup wire, or heavier gauge lead wire could be soldered and crimped and attached to the magnet wire as well. Oh, there, that shows the lead wire. Ah, there we go. So this is the pigtail of magnet wire, several strands per turn. See it there. And then somewhere that is soldered or crimped to a lead wire, which is multi-strand also, but it's heavier in gauge. And so there's the joint with tape around it, of where the magnet wire was attached to the lead wire. And here's the phase separators I spoke about. And then this is a strip that goes around here for bracing. That gives rigidity to this mass of end turns. So if you wrap this bracing strip around here, and then you go through the lacing process of the tie cord, and it laces all these end turns and the leads and the pigtails to this bracing strip around the outside. Bigger machines, this will be laced to to maybe a steel insulated ring that I showed you on one slide in the last lecture, or it can be attached to steel blades that have been welded to the end of the core to support these end turns. So here's some blown up details of the slot insulation. Here you have sometimes an extra liner is used in the bottom of the slot. This is the main slot liner, and it comes it can be formed like this and inserted by hand. There's hand forming machines and there's automatic forming machines, and This is an example of the cuff liner. That's all done by machine. A strip of this stuff goes in a machine and automatically cuts these and forms these and folds these cuffs. Those are little cuffs. You squeeze this together and put it in a slot, and it pops out, and the cuffs center it and space it up on top of the core like that. So a lot of motor companies these days, they don't even weld the lambs together before they insulate. Because if you have a set of loose lambs here that are properly aligned, you put the slot liners in, and that will hold the core and line it up pretty well. And then you insert the windings, and you could skew this core after the windings are put in a proper fixture, and then weld the OD as skewed. That's a very popular process for skewing stators for permanent magnet machines. This is a slot separator. If you have one side of a coil of phase A in here and you have phase B there, this is a slot separator that insulates the two phases from each other, because you might have plus 600 volts here and minus 600 volts here, or something pretty close to that. So you have a big potential difference across any adjacent conductors that would be touching without this slot liner. And this is a top stick or a slot wedge that goes in the top. Sometimes these slot liners are made long. Eliminate this, and you just overlap them, tuck them in here, and overlap them like this in the slot. It's very important when you're inserting coils in an insulated core like this that you don't get any conductors down underneath the slots. That happens frequently. Particularly if you have a bunch of strands, you could make a sloppy mistake in insertion on a production line and get a conductor down behind the slot, and then you're going to fail in high pot, and you have to tear it out and wind it over. Here's a similar arrangement of the same thing as the previous slide. We have a thick top stick in this case that's used sometimes to wedge and force these all to touch each other for better thermal conductivity, and you still have some slot liner material in here to separate the phases. This is another picture of the cuffed core with some of them left out there, and the slot liners or cuff liners are laying beside it. Here's an example of the core that's been fluidized, coated with that epoxy, ready to wind. This happens to be a DC armature. This one here is a case of molded. This is a nylon, glass-filled nylon piece that goes halfway down the slots, and one identical to it goes down the other end of the slots, and so you wind your coils around this. This is a stator on the inside, but this can all be done as a stator on the outside as well. Here's an example of a higher voltage machine that has open slots. See, there's your slots are open, and so you have heavy insulation around the outside, and you have a big thick separator between the two phases, and then it's wound with rectangular conductors that are layered in there. So this is very high slot fill, good thermal situation, and in here they insert an RTD in there, a temperature sensor to put in there to measure the monitor the winding temperature so it doesn't overheat. Then there's a temperature rating system that's used around the world, and I guess it all started in America. It applies to transformers, to electric clutches and brakes. It applies to motors. It applies to all electric devices. Temperature rating classes of A, B, F, H. There's class C in there somewhere also, but it's not in this list. But here's the maximum allowable temperature for devices that are rated at these temperature classes. The nameplate of every motor is going to have this rating, this temperature class on it, and these are peak temperatures in the winding. These are not surface temperatures of a motor, but these are the peak temperatures of the winding, so that you have to use an insulation system, Class A, Class B, Class F, Class H insulation system that's suitable for withstanding these continuous temperatures. I don't know if I have a slide here or not, but there's an old contention or an old rule that for every 10 degrees in operating temperature of an electrical insulation material, you cut its life in half. That's the insulation half-life theory. So even with these temperature, as long as these aren't exceeded, you'll get reasonable life out of the machine. But it's even better to like in my case, I will use, for most of my customers on designs, I will use I might use Class H. I might use 200 degrees C or 220 degrees C insulation systems, but then I'll rate the machine at 155. I'll rate it at Class F, but I'll really insulate it at Class H. One of the problems with these insulating systems is I can get varnish, I can get slot liner materials, and all the materials, sleeving, everything can meet the Class H. The most difficult thing to meet that is epoxies. If you use any epoxies anywhere, it's hard to find epoxies or potting compounds that will withstand those high temperatures. There are some ceramic materials that do, and Toyota uses a material like that in the generator of the Prius. I showed you a picture of it in an earlier slide. It might come up again. But they use that because the stator gets so hot because it's mounted right on the engine and the transmission case. There's a well-documented, well-known failure mode of stator phase windings when they're driven with inverters. And since we're discussing the design of electric machines that are driven by inverters rather than grid power, we have to bring this subject up and talk about this. What happens is if you have an electric motor, any of these three motors driven by an inverter, and if that inverter is quite a distance away from the motor, let's say 50 feet or further, you control the current with PWM. Remember, the currents are controlled all the way down those leads, so you turn the voltage on and off at some PWM frequency. So what this results is standing voltage waves, very high voltage waves, standing waves that oscillate at PWM frequency in these lead wires, these long cables that go to the phase windings. So what happens is that these big, huge voltage waves, 3,000 volts maybe, 4,000 volts. So you can, on adjacent conductors, if there's any fine little weak spots in the insulation of this conductor and it's close to that one, particularly on the first turn of the first coil of each phase, the coils that are out at the end of the Y connection or close to the delta connection. The first turns of the first coils in series for the phase circuits are subjected to this big standing voltage wave that's transmitted through the lead wires from the PWM inverter. So it causes a big potential across any leakage paths there. And what that does is that causes ozone. And ozone is like acid, and the ozone that's created there from the surrounding air causes a very rapid breakdown of this insulation, so you get a turn-to-turn short from that. The erosion is caused by partial discharges. And general purchase heat in the resistant enameled wire appearance after inverter surge application tested after applying a voltage of 1 kilovolt for 11 hours. So you see it's breaking down the insulation on the conductor. So how do you deal with that? Well, so if your motor has the inverter mounted a long ways away, you got to deal with this. And the first thing you do is use bi-magnet wire that's been developed that has insulation that resists these failures. These insulation materials don't eliminate it, they just increase the life a long time. A lot of motor manufacturers will use this inverter duty insulated magnet wire. In addition to that, they'll put sleeving, Teflon sleeving around the first turn of the last coil that's connected to the inverter to insulate it against the next turn. They'll add positive insulation, the Teflon sleeving around there. It takes labor, but it's worth doing on an inverter duty motor. The other thing that's done is to completely encapsulate the stator in an epoxy. A single layer of varnish doesn't quite do it, but another thing that's done is you can do a vacuum impregnate system of the stator, and you can do it 2 or 3 times. That'll probably do it. Or encapsulate it in epoxy, but use inverter duty insulation wire besides. So that's the kind of caution that's taken for high performance motors with long lead wires that use PWM inverters. These are a description of some of the materials that are used for insulation systems and motors and what the thermal classes are. As you can see there, they're all listed there. The 220 degree C rating was always for military. All military stuff is 220 degrees C, and the imide materials that were used for that, like ML varnish and ML wire insulation and Kapton tape. Those tapes were all rated at 220 degrees C, but the DuPont, the company that made a lot of that stuff, they always claimed through their testing that these materials ought to be rated at 240 degrees C. And it took years and years and years, but they finally do have re-rated Kapton and ML wire to 240 degrees C, has been my understanding. So that's about the highest temperature stuff there is. If you need insulation systems higher than that, and some aerospace need it higher, you have to nickel plate the wire and then wrap it with this Kapton tape. But if you need higher temperature than 240, you have to use a ceramic insulation material, and they have those that go up to 3,000 degrees, believe it or not. That's the type of material that Toyota uses in their generator. And there's some really good sources of that, and it's pretty easy to apply. I've used it myself on switch reluctance generators that were assembled inside of a jet engine. This is an example of an encapsulation, of a complete encapsulation of a stator. The company that does this is called NCAP. They're really experts at this. They encapsulate, their system is used to encapsulate the stator in the Segway vehicle. Most of you know about the Segway vehicle that has all those gyroscopes, and it's a 2-wheel personal transport vehicle, and it has 2 high-performance brushless motors in it, and the stators are completely encapsulated in the thermoconductive materials by the process by this company, NCAP. This is this particular picture here is a project I work on. This is a deep sea propulsion motor for a deep sea vehicle that goes down several miles. This motor is made by an American division of Alstom, and this thing is assembled with propeller blades inside of it. It's an outside rotor, a rim brushless motor, and all the parts are encapsulated because this has to go so deep in the ocean that it has to completely, there can't be any voids in there, or the pressure from seawater will go in the voids inside the stator. Then when it comes to the surface, it'll explode from the pressure. But this provides very good thermal conductivity from the conductors through this material to the seawater to cool it. And here's an example of of a stator that's been encapsulated with this ceramic material. You can see there's the aluminum housing with the a core fitted in there with all the windings and lead wires in place, and then it's completely encapsulated with this ceramic thermoconductive material. This is a picture of a typical mold design to pressure cast a stator by transfer molding to completely encapsulate a stator. Let's look at a few of different phase coil types or slots with phase coils. We looked at some of these before. This is these two end ones are similar, and the two middle ones are similar. This is like the first one I showed, but it calls out the components here. This is open slot form wound coils. This is a semi-closed slot with random wound coils, and this is an open slot with form wound coils, the same as that one. Sometimes you have two layers of coils in here. It's rectangular wire. These are the phase separators and the wedges to hold them in. So a better picture of that. Here's this shows the steps of insertion and insulation. So you put, and this would be a random wound slot with quite a big slot opening here. So you put the slot liner in. You put the first one side of one coil in. This is a lap. These are lap windings where one side of the coil goes in the bottom of the slot. Then so many teeth later, according to the span of the coil, depending on the number of bolts, the other side of the coil goes in the top of the slot. So these overlap like this. And so, but before the second coil is put in, you have to put this this coil separator. And when that's put in, you got to make sure that it doesn't get under one of these conductors. It's got to be. That's pretty easy for the girls to use. They use a little wooden stick down the slot, a tool, to make sure they lower that and get it on top of the windings, and that none of these windings creep out over the OD. Then you put the second coil in, and you wedge them in with a wooden stick or a fiber stick like that. This is phase-to-phase insulation, which is very important. Under 200, 250 volts, phase-to-phase insulation is usually not required. It's good practice, but I would say that 220 volt motors, I would put phase-to-phase insulation in, but for 110 volt motors, I wouldn't. And in terms of inverters, 110 volt motors, 150 volt DC, and the 220 volt AC motor, you have to insulate against 300 volt DC. So for higher voltage, the phase coils must be insulated from each other, both in the slots and in the end turns. It probably between 100 and 250 volts. You only need phase insulation in the end turns. You probably don't need them in the slots. So there's the insulation between the phases and the slots. To do this, but in the end turns, you take a sheet of this insulation fiberglass and you slip it between the phases, so you have all of these lapped all the way around the stator, and then you trim them with the scissors. You have to be careful trimming them with the scissors so that you can form and lace these end turns and keep them as small as possible. They should be pushed in there, and this side here touch right up against the stator core. So there's no chance of any of these creeping down and touching any of those. It's hard to show why you need to do that from a picture like that. Now, the form wound coils, or you see how each conductor is rectangular, and each strand is insulated. Each strand is insulated, and then the whole bundle of them is also insulated. So this is a machine that does automatic taping of form coils, and these are only inserted in open slot stators. Some of these are 10 feet long, and other ones are only a foot long. So you can tape these by hand, but they have machines that do this. This is like a toroidal taping mechanism, and this is fed back and forth through there as it tapes all around. So that concludes this lecture. Thank you very much.